In this video, we're going to take a deep dive into the concept of metallic bonding, which is the specific type of bonding that happens only between metal atoms. It's a unique and powerful structure that gives metals their special properties. We'll look closely at how this bonding works at the atomic level and how it contributes to metals being strong, durable, and good conductors of heat and electricity. Then, toward the end, we'll also talk about alloys and explore how they are different from pure metals, especially in terms of strength, structure, and usage. To quickly recap what we already know, metals tend to bond with nonmetals through ionic bonding, which involves a transfer of electrons from one atom to another, while nonmetals bond with other nonmetals using covalent bonds, where electrons are shared rather than transferred. But when it comes to metal bonding with another metal, we call this metallic bonding. Now let's break that down. If we imagine a piece of solid metal, it consists of a giant lattice of atoms, all neatly arranged in a fixed and repeating pattern. In diagrams, you might see each atom shown with its outermost shell of electrons. However, when these atoms come together to form the metal structure, they actually lose those outer electrons. These electrons don't just disappear, they become free to move throughout the entire structure. That's why we call them delocalized electrons. As a result, each atom effectively becomes a positive ion, since it has lost one or more negatively charged electrons. These positive ions are surrounded by this sea of delocalized electrons, and there's a strong electrostatic attraction between them. This attraction is what holds the whole structure together and gives metals their remarkable strength. This entire arrangement is what we refer to as metallic bonding. Because of these strong bonds, most metals have high melting and boiling points. That's also why they are usually solid at room temperature. Another important point is that these delocalized electrons are not stuck in one place, they are free to move. And because they are mobile, they can carry electric current and thermal energy throughout the entire metallic structure, making metals excellent conductors. Now let's move on to another interesting aspect, malleability. Metals are malleable, which means they can be bent, pressed, or hammered into different shapes without breaking. That's how we get things like metal sheets or wires. This flexibility is a bit surprising at first, because metals are generally seen as hard and rigid. But the reason lies in their structure. Since metal atoms are arranged in layers within a regular pattern, these layers can actually slide over one another when a force is applied. That sliding ability is what makes them malleable. However, this is more true for pure metals. If we want something stronger and less likely to bend, we turn to alloys. Alloys are made by mixing two or more different elements, usually metals, or sometimes a metal with a nonmetal. The key idea is to choose elements with atoms of different sizes, which disrupts the regular layering in the pure metal. When these differently sized atoms mix, they distort the layers and make it much harder for them to slide past one another. This increases the hardness and durability of the material. For instance, steel is an alloy made primarily of iron, but it also includes 1 to 2% carbon, and sometimes additional elements like chromium, manganese, or vanadium depending on the desired properties. These extra elements give steel the enhanced strength it needs to be used in demanding applications like constructing buildings, making vehicles, or even aircraft. So to sum up, metallic bonding is the force that holds metal atoms together through a sea of free-moving electrons. This structure makes metals strong, conductive, and workable. And when we need metals to be even stronger or more resistant to deformation, we rely on alloys to get the job done. That's it for today's video. If you found this helpful, please give it a like, don't forget to subscribe, and we'll catch you in the next one.